Good day, friends. Today we're going to solve this problem, the system in equilibrium state, and the given goes like this. Rod AB with a mass of 5 kilograms is attached to the fixed support by hinge A and can rotate in vertical plane. A thread is attached to end B of the rod. The thread is thrown over block C and the load of mass 2.5 kilograms is suspended from it. The axes of block C and hinge A are located on the same vertical, and AC equals to AB, which means their lengths are equal. Find at what angle alpha, this is alpha, between the rod and the vertical system will be in equilibrium. Okay. So what we have here, it is said that we have this kind of block. Yeah, this thing is a block. Then there is some rope attached here and then thrown over this block C, and this mass of 2.5 kilograms is attached to it. Okay, and the entire system is in equilibrium state. And it is also said that C and A points, for example, this is A point, this is C point, those two are located in the same vertical axis. Yeah. And it is also said that the lengths of CA, yeah, let's say this is length, and the lengths of AB are equal. It is said exactly here. Okay, good. Right now, let's make some analysis. Because right now it is said that our entire system is in equilibrium state, which means that the sum of forces equals to 0. And also this thing can rotate, but it is not being rotated. That's why it means that sum of torques is also 0. Okay, right now let's make some analysis. What kind of forces are there in our system? For example, here I definitely see mg, the weight, and also the rope, which is here. The same tension force goes here. If you ask me why, this is the same rope right here. Yeah, it is massless, it is extensible. That's why the tensions from both sides would be the same. It's the same rope. Okay, good. One more thing to note, that here we have huge mg. It will be also straight down because it does not matter at what angle our object stands. The weight goes from the center of mass and it will always be directed toward the ground. Okay, good. What else do we have? As it was said, AB, yeah, this length AB equals to this length AC, which means that these two angles logically, okay, this is not alpha, this is beta, has to be equal to each other. Yeah, beta and beta. Don't look at that. This angle looks larger. If we draw this beta right here, this angle will also look a little bit larger. And I hope that those things are understandable to you. Yeah, why those two angles are equal to each other? Because those two lenses are equal to each other. Okay, good. Right now, we need to break this thing into components. This would be very important. Okay, please try to imagine. I will draw it like this. We have here the end of the rod. I will draw it like this. And this would be, okay, this would be the point A, this would be the point B, okay? And as you can see, if you can imagine it, this mg, in this case, would look like this, yeah? Because if we rotate this thing, just try to imagine it, even if you put your video at an angle, yeah, then you would see that mg looks somewhere here. You would also see that this t is not looking straight up, it's not at 90 degrees, yeah, like this. Instead, it's at some angle, maybe like this, yeah? It looks like it is 90 degrees, but it's not. Okay, good. This is tension force. Okay, what do we have here? Also, we know that this angle is alpha. This angle is beta. Okay. Right now, if we try to break it into components, it would look like this. mg goes here and here. Tension force goes here and up. Okay, but we know that those forces that are parallel to our object that we are trying to rotate, those forces do not count. Those forces cannot rotate. Only the forces which are perpendicular to our system that we are trying to rotate can rotate. But instead, this force and this force, they cannot rotate. Right now, let's try to understand what are these forces. Okay, if we have this kind of case, we definitely know that this is the law of Z. The alpha angle here, mg looks probably here, yeah. Yeah, my wrong drawing. In fact, the mg should have looked like this somewhere. As you can see, those two things are entirely parallel to each other. mg looks straight down and this line looks straight up. That would be the case. So as you can see, this is the law of Z. If you know that from geometry, that's good. It means that if this angle is some alpha, then this angle is also some kind of alpha. And we know that this is the adjacent force, but we don't need it. We need the opposite, which is if this is mg, then this thing would be mg sine alpha. Okay, good. What about this case? This would be much easier because this would be adjacent, which means that this had to be t cosine, but we don't need that t cosine. Instead, we need t sine. T sine alpha. T sine beta. Yeah, I'm sorry. Yeah, pretty good. Yes, I like it. Right now, we know the perpendicular forces that are trying to rotate, and we know that the center of mass is exactly the half of the length divided by 2. And this entire thing, let's call this thing L, just length itself. Okay, good. And our pivot point is right here. which is in this image right here. Good. If you write this law about torques, it would look like this. The sum of torques. The force number 1, mg sine alpha, it is trying to rotate, as if you can imagine it, it is trying to rotate this side. Whereas T sine beta tries to rotate that side. Let's call it T1, let's call it T2. Torque 1 goes clockwise, T2 goes counterclockwise. Let's choose clockwise as positive. T1 minus T2, it equals 0, right? It's equilibrium. Nothing is being rotated. And if we throw that T2 to the other side, it will be positive. Torque 1 equals to torque 2. Okay, we know that formula of torque is force multiplied radius, or distance from the pivot, but we need to remember that this is not just multiplication, this is cross product, which means that the force that is being multiplied to the radius, or the radius that is being multiplied to the force, they have to be perpendicular. So this is F1 R1, this is F2 R2. Good. Okay, right now let's look at this. mg sine alpha is the force 1, and its distance is L divided by 2. So in here we must have a huge mg sine alpha and multiplied L divided by 2. Here this force 2 that is trying to rotate, it's T sine beta. T sine beta, and the length is just the entire length. As you can see, we can cancel those out. We know the meaning of tension force because it is exactly here. It is equilibrium state, which means that those forces are equal to each other. T equals mg. Right now we can substitute it to mg, and it would be just T sine alpha divided by 2 equals mg sine beta. Okay, right now we can cancel those out. Okay, not masses, I'm sorry, gravity, yeah? Okay, good. But the problem is that we do have the angle alpha, yeah? Instead, we are trying to find this alpha. But also there is one more problem, which is this angle beta. We don't know the meaning of it, yeah? So how do we find it? If you look at this case, yeah, if you look at this triangle, yeah, let me note it like this. If you look at this triangle, this is angle alpha, this is angle beta, and this is angle beta, which means that beta plus alpha, yeah, double beta plus alpha must give us 180 degrees. Okay, and we can give the meaning of beta from here. To beta would be 180 minus alpha, and beta would be just 90. Everything is divided by 2, and minus alpha divided by 2. Okay, the meaning of beta is found right here. If we continue it, it would look like this. M sine alpha divided by 2. This thing, mass sine beta goes to 90 degrees minus alpha divided by 2. We have found the meaning of beta. Right now, it is pretty convenient. As you can see, 90 minus alpha, yeah, in our case, alpha is alpha divided by 2, but we know this law. Sine 90 minus some theta gives us cosine theta, yeah, right? Okay, that's why it would look like this. M sine alpha divided by 2 goes here to M cosine alpha divided by 2. Okay, good. But there is a problem again. This is angle alpha. This is alpha divided by 2, right? But there is one very good technique from trigonometry that we know. We know there is a law which is like this, sine to alpha. Yeah, so sine to alpha gives us 2 sine alpha cosine alpha, right? But the problem is, what is our double alpha? Instead, I can rewrite this sine alpha like this. Sine alpha can be rewritten like this. Sine 2 multiplied alpha divided by 2, right? Because those two cancel out, and then we will have sine alpha itself. Good. Then, what should we do? M sine alpha is now turned into this, but if we open that up, it must be double sine alpha divided by 2, and also cosine alpha divided by 2, because it is double theta, as you can see. This plays the role of theta, right? This is theta, this is theta. Okay, good. Good. And then we open that up, m, then we'll have here double sine alpha divided by 2, cosine alpha divided by 2, also divided by 2 here. Here we have m cosine alpha divided by 2, and then as you can see, 2 and 2 go out, cosine and cosine, and then you can have this answer, which is sine alpha divided by 2 gives you m divided by m large, right? Okay, I hope that we didn't forget anything. Okay, and we need to find the meaning of alpha. That's why let's make it like this. This thing has to be arc sine m divided by m. Yeah, and also one more thing which is important, that this is alpha divided by 2, but we need to find the meaning of alpha itself. That's why it has to be double arc sine m divided by m. Okay, this is the answer of our problem. I hope it is pretty understandable to you, and if you didn't, please you write me privately, and I will try to explain it to you. the way that you understand. Okay, thanks for your attention. I hope it was pretty clear, but if it is not, yeah, I'm always open to you. Goodbye. Thanks.